In this particular lecture, we are looking at the second moment of area of waterplane. So when a ship or any floating object is floating, we have the waterplane, which is the surface by which the body is immersed. So if we cut at that waterline, then that is considered as the waterplane. So waterplane has a number of characteristics. It has its area, and also it has a first moment, and also it has a second moment. Second moment is basically the area multiplied by the distance to any particular axis. For example, if this is an area, if we take an element of it, we call it area A, distance y from an axis, then the I for that particular area, I is the symbol for second moment of area. I, because it is just a component, so we've got small I. Then it is the area of that small component multiplied by y squared, which is the distance from that area to a particular reference axis that we're talking about. So for the whole of this area, for example, this is an area of a waterplane or area of a piece of paper, then the I would be a summation of all these small ay squared. Right. So it's okay. This one we keep it in mind because this will go into our naval architecture 2 in chapter 3. We'll deal more detail with this formula and so on. But if you see in the notes that we have now, we also have an explanation about how I, for very simple objects like simple area, yeah, a simple uniform area like a rectangle or a cylinder. Okay, so when do we get a waterplane area of a rectangular waterplane area like this? When there is a barge or a box shaped ship or barge or any floating object, then you see that the waterplane area here is a rectangle. So of course the area is L times B, yeah. But what we are interested here is not the area itself, but we are interested in the second moment of area of this waterplane. So when we take second moment of area, we deal with, we must look after its reference, the reference axis from where the waterplane, the second moment is taken. So there are, we can take the second moment of area about midship, yeah, where it is as if that this area is rotating about this axis here. Or we can take the second moment of area about the center line, where the area is rotating like this, yeah. Or we can take the second moment about this axis, xx, yes, where this thing is supposed to rotate like this, yeah, about this axis. So these are a number of ways. Of course, we can take any axis, we can put it. But normally there are three axes that we normally see being used. For example, if we take about IXX, which is this axis, then this is the formula for a rectangular waterplane area only is 1/3 times L times B cubed. And if it is about this axis, which is the center line, this is called IT, the transverse center, the transverse second moment of area. Okay, it's the same as ICL, I about the center line, and it is 1/12 times L times B cubed. And if it is about this midship, then it is the IL is the same as I. This is longitudinal second moment of area. It's the same as I midship is equal to 1/12 times B times L cube. Okay, so you notice that this is B cube, this is L cube. So that means IL is very big because it's L cube, and IT is not so big because it is B cube, L times B cube. This one is B times L cube. This one you see that how to remember. L is here. So when you are taking about this axis, then L is cube. When you take about this axis, then B is cube. Yeah? Right. For a cylinder floating like this, then the waterplane area is just a circle like this. So for a circle, the second moment of area of about this axis or this axis is the same. So IXX is equal to IYY. and the formula is pi d4 over 64. So you just have to remember this formula, and this one, particularly for calculating of ixx, iyy, it, il. This is the same as il, this is same as il or it, all the same. So il is equal to t is equal to ixx is equal to iyy for a circular water plane area. Right. And then another thing that we need to know is a parallel axis theorem. Parallel axis theorem says that when we say, for example, we have this circular water plane area here. So there is a cylinder here, but so we can find its I about its own axis, which is like this one. So I about its own axis is pi d over 4 over 64, where d is just the diameter. Yeah, so this I of this. I put it small because it is a component. So if you say that actually I'm not interested is I about this axis, I'm interested I of this about this AA axis, then theorem, parallel axis theorem says that IAA, I about this axis, is equal to IYY, which is I about this axis, plus the area multiplied by y squared, where y is the distance between this axis and this axis. So in this case, IAA is IYY plus area times y squared. So the IYY is this one, pi d4 over 64, plus area pi r squared times y squared. So this is IAA here. Okay. Now consider if it is a catamaran with rectangular hull. So you have like these two, one hull here and one hull here. So going in water. So if you see the water plane area, then it will look maybe something like this, simplified into a rectangle. Simplified into a rectangle like this. So if it is a two rectangle like that, so if this is L, yeah, the length here L, we put small l, and this is B for the small breadth here, because the catamaran breadth B is this one, this big one, yeah. So what we do is to find the I about the center line, which is IT about the center line. IT is equal to I about the center line. Okay. So you want to find I about this reference axis, then you have to first find its own I about that axis, and then you bring it here by adding AY squared. So ICL, IT is equal to ICL, I, which is I about this axis, plus AY squared. And then since this is only one side and there are two sides, so this one you need to multiply by 2. And in the naval architecture, you see in my class, this when we say 2, we put in the circle like that, it means it's 2 times because there are 2 hulls. Then we can say, oh, this 2 is actually for 2 hulls. If there is only one single hull, like this one, there is no 2. Yeah? But since we are taking both sides, bringing it into the center line, so we multiply by 2. Say if there are 4 hulls, 1, 2, and then we have 1, 2 here. Then we multiply by 4. Okay? So I plus AY squared times 2. So you see for I for this is 1/12 times LB cubed plus the area of this L times B times Y, which is this distance squared. And the whole bracket is multiplied by 2 because of the 2 hulls. So this is how we calculate the I, the second moment of area of the water plane. And this is very important for calculation of BMT, BML, and MCTC. Those are the hydrostatic particulars which are very important for the calculation of stability. Which is in the next video, you're going to see how we use I to calculate BMT, BML, and MCTC. MCTC is moment changing trim 1 centimeter. BML is distance from center buoyancy to metacentric to the metacenter, longitudinal metacenter, and this is from center buoyancy to transverse metacenter, the two metacenters in the ship. Okay, metacenter, we have two metacenters. B, there is only one. G, there is only one. But metacenter, there are two, MT and ML. And MCTC is a moment changing trim 1 centimeter. We need to have that value as hydrostatic particulars as well. So that's the end of this. We'll continue with that video after this.